Hello everyone, welcome back to my channel. So the next topic is Hall effect. Okay, this is one of the important derivation and it's frequently asked question. Okay, so what exactly is this Hall effect? Okay, Hall effect is used to determine whether a semiconductor is N-type or P-type. Okay, to check whether this semiconductor is N-type or P-type, we can use this Hall effect. Next is to find the carrier concentration. That means either electrons or holes. What are the majority carrier concentrations? We can know because of this Hall effect. Next, carrier mobility. How these electrons and holes move, everything we can learn from this Hall effect. Understood? So what are the uses of this Hall effect is, first thing, it is used to find whether it is N-type or P-type. Next, to find the carrier concentration, and next its mobility. Alright, I think this is clear now. So next, what is its exact definition is what we will see here. Okay, see, if a metal or a semiconductor carrying a current I is placed in a magnetic field, transverse magnetic field, or a magnetic field B, magnetic field is always given by the letter B. Okay, and electric field E is induced in the direction perpendicular to both the current and magnetic field. Okay, so a magnetic field direction. This phenomenon is called Hall effect. So that means, see, if a semiconductor, it is carrying some current I, it is placed in magnetic field. That means a electric field will be created in some direction which is perpendicular to this both current and magnitude. Okay, understood? Electric field is created because of this too, and that electric field will be perpendicular. That means 90 degrees to this current and magnetic field. So that phenomenon is called as Hall effect. Okay, so next, this is the diagram of the Hall effect, schematic of Hall effect setup. Okay, suppose this is you are taking in XYZ plane. Okay, and this is a semiconductor. So see, this rectangular plate, if we consider it is made up of N-type. Okay, and this is the current, these are the electrons, and this is the thickness. T is the thickness. Okay, now we will see its derivation part. Okay, consider a rectangular plate of N-type semiconductor carrying a current I along the positive X direction. Yes, X direction is this one. So current is in this direction. Okay, next, the current carriers, which are free electrons in N-type semiconductor, have a drift velocity Vd in the negative X direction. So here we are telling the current carriers, whatever are present over here, that means the free electrons. Since obviously in N-type semiconductor, the majority carriers will be electrons, right? So based on that, those electrons will have some drift velocity. Drift velocity is nothing but they will have some speed. Okay, that speed, drift velocity is given, denoted by this Vd. So that speed will be in the negative of the X region. So see, this is current is there, electrons are there. So this they'll have an speed in the opposite of X direction. So X direction is normally this one, no? But these electrons will be moving in the opposite direction. Alright. So let magnetic field of strength B is applied along Z direction. So we are telling this magnetic field is applied over this direction. Magnetic field is represented by B. So obviously what we told, electric field will be set up in perpendicular to this one, right? So this is 90 degrees. Here the electric field is produced, which is perpendicular to magnetic field and the current. And the current is in the X direction. Okay, understood? So what happens is, see, under the influence of magnetic fields, the electrons experience a force known as Lorentz force, which is denoted by letter Fl, and it is given by Fl is equal to Be V of D. Okay, because of this magnetic field, what happens? These electrons will experience some force. That means there will be some movement coming in those electrons. That is called as Lorentz force, and that is denoted by the letter F of L, and it is given as F of L is equal to BeVd. E is nothing but the charge of the electron. Okay, this is the first point which you need to remember. Alright, after this, see, because of the Lorentz force, the free electrons will move in the negative Y direction and collect at the bottom surface, and the positive charges accumulate at the top surface and negative charges at the bottom. As a result, potential difference develops. Obviously, right, these electrons are moving in this direction. Electrons will be having negative charge and the positive charge will be accumulated on the top of the surface. So here there is negative charge on the top. All the complete, this whole plate will be of positive charge. Okay, electrons will be on the bottom. So here negative charge is there on the bottom of the plate and on the top there will be positive charge. That means in between these two there is some potential difference between two points, right? That is called potential difference. So there is some potential difference occurring in this plate. So that potential difference between the top and the bottom surfaces is called as Hall voltage. Okay, difference in between those charges. So that is called as the Hall voltage VH. You have to remember this denotation VH. Okay. Next, this voltage establishes an electric field. Like I said, that will establish some electric field EH, which is called as Hall field. Okay. This field exerts a force. That force is, formula is E into E, right? So that is on the electrons, which balances the magnetic force. So EEH is equal to this one, BEVD, which we got in the previous one, the Lorentz force, BEVD, right? So that force is EEH. From this we kept that over here. Okay, from this EE will be cancelled. So E of H, that is called Hall field, is B is equal to E of H is equal to B into V of D. So consider this as first equation. Okay. So now this is the D is nothing but the distance between the top and the bottom surfaces. Okay. So this E of H can be given as V of H, voltage, electric field, that is given voltage and the distance between those 2 points. Voltage by distance. So if you equate these two equations, E of H, and both are same, right, on the left hand side. If you equate these two, you will get VH of D is equal to, okay, VH of D is equal to BVD. This one, VH of D is equal to BVD. Okay, you are equating these two. So from this, V of H is equal to D going that side, it will become BV of D into D. Consider this as third equation. Okay. Now if we say, if T is the thickness of the semiconductor in the Z direction, so the current density, this is the formula of current density. J is equal to rho into Vd. Okay. Rho is the resistivity. J is equal to rho into Vd. So this can also be written as J is I by Td. So in current density derivation, you will know how we have derived this. Please, there's a video on this current density. Please check back that video. So J is also I by Td. This is J. Don't get confused. J is I by Td. Okay. So deriving this, J is rho Vd, what I said, I by Td. So rho Vd is equal to I by Td. According to this. From this, Vd is equal to rho going to the denominator, I rho Td. Consider this as fourth equation. Substitute equation 4 in equation 3 we get. So that is Vd. Okay, Vd value just we are substituting there. So what is this third equation? Just for your understanding, I'll show one more time. Third equation is Vh is equal to BVDD. So in the place of Vd, we are substituting this one. So see, Vd, we are substituting this. Vh is equal to B into, in the place of Vd, substitute this one into D. Okay. So obviously Dd gets cancelled. Vh is equal to Bi by rho T. Okay. This is the equation 5. So from this, rho value is, Vh will go here. So Bi Vht. So rho is the, I said resistivity in the previous one. So that is nothing but charge density. Okay. Rho is charge density. Now we will see how to derive Hall coefficient in the upcoming video. Okay. I think this is clear till here, right? Thank you.